Yes.
Good morning to all of you, and I'm very pleased to be present in this virtual summer school. Now, I have tried to speak about some non-traditional techniques to study environmental assisted corrective phenomena, with many examples of some laboratory activity that we carried out in order to study the hydrogen embrittlement phenomenon using non-standard techniques. Now, we can say there is the traditional environmental assisted cracking graph in which is presented that environmental assisted cracking is due to the synergic effect of an environment on the susceptible metal and applied stress. Generally, hydrogen embrittlement or generally either environmental assisted cracking are studied by means of traditional techniques, standardized, that use specimen with standardized dimension and that generally are machined from the materials that are of small dimension, and generally it's not considered some critical aspect as the S-produced surface. Time to trigger is generally a problem that generally is bypassed using slow strain rate test in a traditional test, or for example in this picture this is an autoclave high pressure test using slow strain rate, but there is not always to be considered the effect of localized attacks or the variation in stress and strain condition, and it's difficult to study the presence of wells in the steels. Now we can see some example. This is an example to use the has produced surface in pipelines. Why use has produced surface in pipe? Because generally the machining, the hot working, leave on the pipe a scale of oxide that enter in exercise and can change the behavior of the surface, that is the surface is the environment. The first interaction with the environment is the surface. For this reason, it's important that the surface was strictly characterized by the test. In this case, we have modified a specimen as a tensile test specimen using a section of pipe. It could be seen that there is a reduction in the thickness of the pipe, preserving the inner surface that was the surface that is in contact with the aggressive environment. We have done some development of this method using, for example, a taratur in this mode in order to have a relation between the strain on this part of pipe in the external and the inner surface, in order to have a relation between the external strain that correspond to the inner strain, in order to have, using the extensometer in the external test surface that was machined, it was possible to apply the extensometer to have the real strain in the inner zone that was that interested to us. This is the specimen before the test, and this is the specimen after the 1 month of test in NACE solution with H2S1 bar. It is possible to observe a close-up of the inner surface with the scale, the original scale, and the corrosion product. In this case, we have no cracks from the has produced surface. This is an example of the localized attack generally, stress corrosion cracks start from localized attack. This is an example for a martensitic stainless steel in chloride in the H2S environment. And this is a particular case. This is a steel very similar to the steel presented by Professor Torribo in the presentation before me, in which there is the cracks that started in a very low aggressive rain, atmospheric rain, that is started from localized pit due to the presence of hot mill in the surface of this high-strength steel for post-compression concrete structures. And this is another example in which there is in the near-neutral stress corrosion cracking. This is a particular form of stress corrosion cracking that was observed on buried pipeline after many years of exercise, in which there is a particular condition in which there is some localized attack in a generally corroded surface. And the difficult to make some tests of this kind of stress corrosion cracking stress corrosion cracking phenomena is to have some surface that is similar to the field, because there is necessary to have this presence of simultaneous presence of localized attack and generalized attack. In this case, we have done some experiment in order to have some electrochemical pre-corroded surface that reproduced the condition very similar to the field, and we can use this pre-corroded surface for slow bending test, for example, in which we have the initiation of cracks in this localized attack, and we can try to reproduce this phenomenon using full-scale test. This is the procedure of pre-cracks making on the pipe, a 48-inch pipe that was buried for 1 year using this pre-corroded electrochemical pre-corroded surface, and buried and will exercised for 1 year using 1 cycles day of pressure variation. And at the end of the test, we can see that from the localized attack, there was the presence of some micro cracks. But I can see that our experience with non-traditional tests, more interesting, is in the hydrogen embrittlement, and in particular we focused our attention of hydrogen embrittlement of pipeline steel cathodically protected. Why to study the hydrogen embrittlement in pipeline steel cathodically protected? Because this is a particular case of hydrogen embrittlement. Pipeline steel are immune to hydrogen embrittlement and the cathodic protection. There are thousands of kilometers of pipeline protected, cathodically protected without any problems. Also in the presence of very high potential cathodic protection, overprotection, and very high constant load. But there was some hydrogen embrittlement failure that can take place, for example, in the presence of alteration of the microstructure. This is so-called hard spot that was found at the end of the 60s and 70s. This is an old case. Now, in the past, we try to study this phenomenon, reproducing in laboratory an artificial hard spot. This is this experiment was done on a very thin specimen, 1 millimeters. The micro hard spot was obtained using a CO2 laser, high power laser, and quenching with water. And this is the micro hardness map that evidence the high hardness inside the artificial spot. Now we use this very thin specimen with the artificial spot to make a permeation, hydrogen permeation test under a constant load. This is the end of this experiment, in which the specimen failed in the correspondence of the hard spot. But the most interesting aspect was the hydrogen visualization using the photoelectrochemical technique. Just a few words to illustrate the scanning photoelectrochemical microscope technique. That was a technique that was developed in the 90s, in the end of 80 and the first 90 years in the Polytechnic of Milan and the Center of Study of Electronic Process of CNR in the Polytechnic by Dr. Razzini and its groups, in which it was found that the photoelectrochemical response of the passive film of carbon steel, but also of other metals, was influenced and increased by the presence of hydrogen. It was possible to realize this kind of equipment in which the specimen works in a photoelectrochemical cell, in which it was, this is a traditional Devana-Tastajewski permeation cell, in which one side of the specimen is cathodically charged by hydrogen, and the other side is in an anodic compartment in which there is a alkaline solution, and in which is without hydrogen measured the anodic passivation current, and in the presence of a laser light, the photo response of this passive film. Now it was found that in the presence of hydrogen, the response of the photoelectrochemical response of the passive film increased. And though is done, this is very simple that make a light black, a very thin laser light that was scanned on the specimen, on the surface of the specimen. The difference between the anodic current in the presence of absence of the light was attributed to the effect of hydrogen on the passive film on the specimen. In this way, it was possible to realize point by point a photoelectrochemical map that can evaluate the evolution of hydrogen inside on the exit surface of the specimen during charge or discharge. Here we can see the accelerated photoelectrochemical maps of this Earth spot. The photoelectrochemical response was changed in false color, and we can observe that hydrogen increased in the external zone than the artificial spot, because inside the artificial spot there are many traps that trapping the hydrogen in the first time of permeation, and we can observe that there is an increase of hydrogen solubility in high energy traps, in which it is not possible to exit from hydrogen in the first time, in this case 3 hours, of hydrogen charging, that we can think that it is responsible by the delayed fracture of the hard spot. With the time, there is a saturation of the signal because hydrogen become to exit only from the hard spot. The DX was also used, to study a particular, a unique case in which the hydrogen failure there was a hydrogen failure in a bagged pipeline without any microstructural alteration. There are no hard spots in this case, but in this case it was a rock that was in the backfield of the pipeline that make an indent in the pipeline during the realization of the pipeline. In this case, it was broken the coating, and cathodic protection start to work and to there was the evolution of hydrogen. In this zone, there is a compressive zone, and it's not possible to entry of hydrogen. And in fact, the hydrogen fracture was started from the inner of the pipe after about 20 years from the realization of the pipeline. It was necessary to have 20 years to have a hydrogen critical concentration in the most tensioned zone. That was the inner of the pipe. It could be for the metallographic section of the defect with the presence of hydrogen embrittlement cracks and some other stepwise cracking, because it was the steel was a ferritic perlitic banded with an old pipeline with manganese sulfur inclusion that makes this stepwise start, and this is the hydrogen embrittlement crack due in the most tensioned zone in the inner of the pipe. This is the radiography of the defect. Now you can see that our laboratory test in order to simulate a similar condition that was has illustrated the rocks, but it was necessary to have a continuous straining of this deformation indent due in field by the backfield assessment soil assessment during the time. Then for us was easy to reproduce the defect, but only in the condition. This is a part of the pipe, this is an indent, and it was possible to realize a similar defect that is observed in field, but only when the hydrogen was supplied for in the inner and not only by the external surface of the pipe. It's good due for two effects. The one is the time. It was not possible to make a test of 20 years, and also we have to evaluate the hydrogen diffusion, and we consider that the time used for to permeate was sufficient to have a condition of crack. We cannot observe this effect. Now we have hypothesized that hydrogen does not permeation from the pipe by a transversal mode, because in this condition there is a compressive stress, and in compressive stress the hydrogen diffusion is obstaculated by the stress by the applied stress, and we find that we hypothesize that hydrogen can arrive in the high tensioned zone by means of longitudinal diffuse. This was due also by the particular microstructure that was banded, oriented perpendicular on the hydrogen diffuser. And the question was how it's possible to evidence this longitudinal diffusion. We can try to use the photoelectrochemical image also to evidence the effect of load on hydrogen. We can see this an experiment on a simple bending in which it's possible to see by the film that there is an increase of hydrogen when there is a plastic deformation. When there is a plastic deformation, it is possible to observe that there is a concentration of hydrogen in the most tensile, plastically deformed zone. And this is another interesting image obtained always with the photoelectrochemical image. The steel was the same of the field failure, in which it's possible to observe the effect of stress concentration. In this case, we make a hole in a very thick specimen, and we from this hole make a fatigue cracks. And after this, we have loaded the specimen using a constant load at the 50% of the yield strength of the steel. We can observe the photoelectrochemical image in which it's possible to observe a high concentration of hydrogen at the crack tip. And this is obvious results. But the most interesting is the delocalization of hydrogen in the plastic radius from the crack tips, and the escape of hydrogen along the banded of ferritic perlitic. In this was another suggestion that the longitudinal diffusion of hydrogen was very interesting. And also possible to evaluate the longitudinal diffusion of hydrogen inside the steel. We can try to make some measure from specimen take from different orientation on the steel, but we have not obtained very interesting value. Why? Because generally the thickness of the specimen are very higher in comparison with the grain size, and the value that it's possible to obtain of the hydrogen diffusion coefficient using the traditional permeation techniques is able to well evidence the effect of the anisotropy in the diffusion of steel. Now we can try to make a simple experiment using the photoelectrochemical test, in which we use a specimen with two windows of different dimensions. We use a very small entry side windows and a very large exit side window, for which it's possible to observe the transversal hydrogen diffusion, but also has hydrogen escape from the perpendicular direction and go in the longitudinal direction. This is my home assistant. Silent. And we have to make the photoelectrochemical maps in the external zone for two kinds of steel. One is the steel banded silence. Banded steel with a large band of ferritic perlitic, and the other is a high strength steel with a very fine banded of acicular ferrite and perlite or bainite inside this band. This is the evolution of the charge of this two specimen, and this is the fast color image in which is very clear the effect of microstructure of the steel on hydrogen diffusion. This cycle is the entry windows, and we can see that the low grade high grain size banded ferritic steel have a large diffusion, longitudinal diffusion. This is a distribution of hydrogen distance from the entry windows, and we can observe that there is a strong orientation. This is an ellipse, not a cycle, because there is a preferential diffusion of hydrogen in the banded direction. In the very fine microstructure steel, is possible to observe that the longitudinal effect is very smaller, and hydrogen exit is concentrated in the zone perpendicular to the entry zone. Now we can say some experiment of the effect of load on hydrogen diffusion. We start for constant load. Constant load, that was the replica of some experiment that was done in the 60s by Bockris or Latanesian. That was all the data, and this is in agreement with this result, in which it's possible to observe an increase of hydrogen permeation flux, steady state flux, when we applied a constant load in elastic field. When the load is applied in plastic field, there is a complex effect in which we have a sudden increase of the anodic current, followed by a strong decrease. But after a transition time, it was possible to observe that the steady state, that the hydrogen flux reached the steady state. What was due to this effect? It was attributed to two effects. The one is the anodic current, because we cannot separate the effect of passive anodic current from the hydrogen permeation current. When we applied a load in constant load in plastic range, we have a rupture of the passive film that was immediately reformed, and this corresponds to increase of the anodic current. This is only another effect that was in the passive that suddenly is in contact with the anodic compartment that make immediately oxided. This is the increase in the initial sudden increase of anodic current. But this effect, the decrease of passive, is observed only when hydrogen is present, not in the experiment that we conduct, used only the anodic in order to separate the effect of the anodic passive current from the hydrogen formation current. This effect was due only to hydrogen that was trapped for the due dislocation that was generated by the applied stress. We can see that there is a recovery of the permeation flux of hydrogen, hence these new generated traps were filled by hydrogen, and the time to reach the steady state depends on the value of the applied stress. What happens when the load is not constant but is continuously deformed specimen? We can observe this effect using this low strain rate test, in which we measure the variation of the permeation current, subtracting the contribution of the anodic current, using different strain rate. It is clear that at very high strain rate, 10⁻⁵, second -1, is high for hydrogen, not in general for mechanical characterization, the trapping effect of hydrogen prevails. When the strain rate decreases at times -6 or 10⁻7 sigma-1, there is a equilibrium between the new traps generated by dislocation and the hydrogen saturated of these traps. So we observe a practically constant hydrogen permeation flux with the straining of the specimen. And here we can see the more recent result that we obtained, in which we try to measure the effect of the applied load, not only in a constant load or constant strain rate, but during a fatigue cycle. We can observe that there was two effects. One is in the not stationary condition, on the apparent coefficient of diffusion of hydrogen, and it could be observed that we have done this test using a constant apply a variation of the load of 10% of the tensile yield strength, constant frequency of time might 2 Hertz, and obviously 10 hydrogen cathodic charge. And we can observe that there is always a decrease of the apparent hydrogen diffusion in the first instance. In this case, we start to cycle the specimen, and when after we have cycled the specimen, start to charge of hydrogen in order to evaluate the apparent hydrogen diffusion coefficient. The result was that the apparent hydrogen diffusion coefficient decreases with the increases of the applied load, and there is a strong decrease when the condition change from the elastic field to plastic field. In this case, we can try to analyze the effect of the cycle on the hydrogen permeation steady state flux current. These values were just this was eliminated the contribution of the anodic passive current, and there is the effect of change of the amplitude of the tensile, of the maximum tensile strength. You can see the red curve, it's from not load to 55% of the tensile strength, and just increase it to 55 to 90 to 90 to 100 to 100 to 110. And we can see that increasing the maximum load of the fatigue cycle, there is a trapping effect that for depth and the time to reach again the steady state values increased as the applied maximum load increased. And this is an interesting effect, that is that after a steady state, after a transition, the steady state value reach again the value before to increase the hydrogen permeation. That was demonstrated that this effect was due only to the generation of new traps, and when the traps were filled by hydrogen, the fatigue cycle did not influence the hydrogen diffusion inside the still. We can try to relate the hydrogen permeation parameter as the hydrogen apparent diffusion coefficient in absence of load to the hydrogen embrittlement susceptibility using a traditional low strain rate test. And we can find that there is an increase, for example, of the hydrogen embrittlement susceptibility in high strain, because there is a strong effect of strain rate, increasing the hydrogen diffusion coefficient, but there is also an effect of the microstructure of the steel, because in this case we have some ferritiperlitic steel that we can observe a linear relation between the average hydrogen diffusion coefficient with the hydrogen susceptibility, embrittlement susceptibility. But we can also observe that if we change the microstructure of the steel from ferritiperlitic banded steel to temperate martensitic steel, for the same hydrogen diffusion coefficient, we have a totally difference in the hydrogen embrittlement. The temperate martensitic steels are either resistance to hydrogen embrittlement than this kind of steel. This is confirmed that the hydrogen embrittlement effect did not depend only from the hydrogen concentration, but also by the intrinsic susceptibility of this kind of steel. In order to evaluate the effect of the steels, we have done some tests using slow strain rate traditional test and considering the what we call it the critical potential. Critical potential was the applied cathodic potential, in which we observe for each steel and for each strain rate the first hydrogen embrittlement effect visible on the fracture surface as brittle area or secondary cracks. We can observe that we have two different maps for different microstructures. This is for banded ferrite perlite or ferrite perlite martensite steels, excuse me for my bad English, and this is tempered martensitic steel. We can observe that the critical potential to have hydrogen embrittlement depends strongly from strain rate. At the very low strain rate, it's not possible to observe difference between the steel because there is, or for very low potential in which it's sufficient, very small concentration of hydrogen to have hydrogen embrittlement effect. In high strain rate, it was possible to observe this between the steel and the tempered martensitic steel have a higher resistance that was possible to observe using very low critical potential to observe some hydrogen embrittlement effect. But also it's interesting to see the effect of the tensile stress of the steel, because it's not as expected. We observe a linear increase of the hydrogen embrittlement susceptibility with increasing the tensile stress, because generally for banded ferrite perlite steel, the increase of the tensile strength is obtained by reducing the grind size, and a reduce of grind size is beneficial in order to is beneficial on hydrogen embrittlement resistance. At the increase of the susceptibility to hydrogen embrittlement with the tensile strength is observed only when in the steels there is accelerated cooling that introduced by NITE or not tempered martensite in the steel that are hard zone, that are higher susceptible to ferrite perlite to the hydrogen embrittlement. But what's the limit of this traditional test using in this mode? Is that the hydrogen effects are visible only after the netting. In this condition, this instability, the condition, avoid the possibility to evaluate the stress strain field. For this reason, it was developed as a slow bending test. Why slow bending? Because using the slow bending, it's possible to have strain condition with high plastic deformation without to have the necking. And it was possible to have a better knowledge of the stress-strain condition, for example, using experimental tests or finite element modeling using, for example, deform 2T, that there is a code for plastic working of steel that is good for very high plasticity and high deformation materials. We can see, for example, in the simulation of 3-point bending and the experimental evaluation of the strain in the specimen at different displacement of the grip. It's possible to observe that there is different strain rate in the elastic and the plastic field, and by means of the SPEM simulation, it was possible to have an idea of the, for example, effect of the cold working of the different steel in order to have the distribution of the strain inside the specimen as a function of the distance of the symmetry plane of the specimen. This is an example of for 2 steel, a very low yield strength steel and high strength steel, with a difference between one and another distribution of the strain. And this is the effect for the same steel from the distance from the center to the other position of the specimen as a function of the displacement of the grip. In this way, it's possible to realize some slow bending tests using different rate of displacement of the grip in order to have a controlled strain rate of the most of the central zone of the specimen. And we use this test for characterize unconventional specimen. This example is, for example, a longitudinal weld. We have removed the over metal, we have cut some specimen, and we have make some tests in air in order to evaluate the strain condition in the upper surface of the specimen, and make some tests in the presence of hydrogen cathodic charging. We can see 2 different results for 2 different welds. In this condition, there is a concentration of the strain in the coarse grain zone, in the heat affected zone, that initiated a hydrogen embrittlement crack that propagate for only mechanical condition. Here was reached the K with 1, and it was a Brattle propagation, mechanical propagation. This is the similar steel, but in this case, the welding was changed the condition of welding in order to have a more uniform strain distribution, and at the end of the test, also in the presence of hydrogen, no hydrogen embrittlement effect was observed on this welding. The slow bending test was also used to characterize another important effect of problems of pipeline, that is external damage. External damage is the first causes of damage of buried pipeline in Italy, because sometimes there is not attention to the presence of a buried pipeline, and there is some work in which the excavator damages the pipe. What's happened when there is external damage on pipe? There is several effects as stress concentration, decreasing of pipe thickness that increases the stress, cold straining and hardening of material that increase the hydrogen embrittlement susceptibility, and in some cases also the presence of microcracks in this high straining material. This is an example in which there is a delayed hydrogen cracking of the damaged pipe that was damaged and remain because the damage was not signalated to the authority in cathodic protection for some time, and hydrogen embrittlement take place from the damaged zone, and this it is possible to observe from the fracture the presence of the damage and the strongly altered microstructure in correspondence of the defect. Now, the problem is how it's possible to study this phenomenon. This is the most complex method. This is a courtesy of Centro Studi Materiali of Rome, in which this is a simulator that is able to replay exactly in reproducible mode the defect obtained by an external excavator. Now we have done some defect on a buried pipeline that were exercised for with 1 cycle day of pressure fluctuation for 1 year in cathodic protection buried condition, and this is the result in which probably presents some cracks initiated from the defect. But this is not a test that we can repeat it for many times, and we can try to develop a laboratory test simple. In this kind, we used the defect obtained by the simulator that were cut in different 3-point bending specimen, and one was tested in air with a slow bending test in air, and the other in solution simulating the moisture of soil with a cathodic protection not very high, minus 900 millivolt with respect calmer electrode. We can see 2 different curves in the possible to observe that the plasticity of the specimen. In the presence of hydrogen, the situation is quite different. We can see the initiation of cracks that propagate by means of the plastically strain, assisted by plastically strain. If we stop the strain, the hydrogen cracks stop to propagate. In this way, it's possible to quantify the effect of hydrogen considering the ratio between the load at the end of the 50 millimeter eclipse displacement and the maximum load in the curve. This was reported in function of the position of the specimen with respect to the defect. It was possible to observe that in air the defect also did not influence the mechanical resistance of the specimen. But in the presence of the hydrogen, some defect that we can find that was the worst condition, the first impact, there is no effect or very low hydrogen effect, because in this the steel remain in compression condition. The worst condition was in this position in which the hydrogen embrittlement effect as higher, and the hydrogen embrittlement effect decreases with the distance from the initial impact. This is interesting results, but they have also another problem. It is not possible to quantify the hardening of the specimen and the effect of this cold hardening of the specimen and the geometry of the defect with the hydrogen embrittlement. For this reason, we have done some tests using a small simple geometry of defect obtained by simple compression using different depths of this compression in order to have different called straining of the specimen. We have done this defect on part of pipe, and this part was divided in two specimens, in which one was tested in air and the other in the presence of hydrogen. It could be seen that there is a almost linear effect of the reduction of the specimen thickness, that increase of the cold hardening of the specimen increase the hydrogen embrittlement. But the most interesting is the possibility to, in this case, because it's a simple geometry, to reproduce by the finite element model the straining of the specimen during the realization of the defect, and after the realization of the defect during the slow bending, that is a similar, not the same, but similar condition of the external damage. This is the external damage, the strain effective obtained during the external damage, and this is the condition of the expulsion of the defect due to the inner pressure of the pipe. In this case, we can see that there is a decrease of the compressive in this zone, and the compressive decrease the high strain in this zone, and there is an increase of tensile in the compressive zone in this part. The possibility to use the program diffusion was used in order to evaluate the effective stress strain during the slow bending, and obtain a strain effective maps on the specimen. Now we can observe this are the map of the strain of the specimen with small depth or very high thick defect, and we can say the strain deformation before the slow bending after the end of the slow. Here is the representation of the maximum strain in the external zone of the specimen with different thickness of the specimen. This green is this part in which you can see that the hydrogen embrittlement, the deformation of the specimen is distributed in all the external zone, and in this case the eye deformation is concentrated in the center of the specimen. Now it's possible to observe that there is a good correlation between this result and the fracture aspect of the specimen. In this case, there are small cracks that was distributed in all the deformed zone, plastically strained zone. In this case, there is only one very deep cracks in the center of the specimen, in according with the eye deformation area. In this way, it is possible to reproduce the real condition of straining and the condition, the effect of this straining of hydrogen embrittlement effect. Now is another example. In this case, this is the defect are smaller, but the still were higher in mechanical characteristic, and we can see the simulation, that is the same image, and the transparency is the metallographic aspect section of the specimen. After the test in air, we can see that there is a very good accord with the form the final shape of the specimen and the simulation. And it is possible to observe that in cathodic polarization there was the presence of cracks, and these cracks follow the deformation strain, the strain path evidenced in the SPEM simulation. Now, as conclusion, I can see that unconventional tests like slow bending permit to study the susceptibility to hydrogen embrittlement on different materials, and that it is possible to analyze different aspects like the has-produced surface, pre-corroded surfaces, presence of different cold hardening, stress intensified effect of weld, and for this reason, for example, slow bending is an effective tool to study the hydrogen embrittlement. Thank you for your attention.